You want to go run through real fast? Huh? You want me to run through real fast?
Yeah, why don't you try that? It's still on.
Do that real fast.
There you go. That's on.
This is dangerous coming here. I should buy insurance. What are we eating today?
Give one more.
If you stop at about quarter till and take questions for maybe 5 minutes, there's a class after here that starts coming in at about 10 till.
Okay.
I don't know if your talk will go that long, but some people have been going over the classes.
Gotten late. Okay. I'll keep that in mind. Thank you.
Do you take attendance for this class? Pardon? Do you take attendance for this class?
They sign some kind of sheet, and then we send it to the Smithsonian, and it's going to be preserved for.
I got course there.
Can I get bonus points on the exam for being here?
Yeah, that's a good question. It depends how much you get. If you get above 90, no bonus points. If you get below 10, I can give you 5 grace points. Okay, let's get started. Hey, is this fine? Okay, perfect. Thank you all for coming today. Good afternoon. So please join me in welcoming Aaron Stein. I should say Dr. Aaron Stein. He has already finished his Ph.D. He finished his master's and Ph.D. in electrical engineering and computer science from the University of Michigan. In 2016, Aaron published his doctoral thesis entitled The Design and Effect of Power Electronics on Vibration-Based Energy Harvesting Methods. He currently holds 2 positions. He is a postdoctoral research associate at Dartmouth College. I have to be careful how I pronounce it. George is going to catch on me. And the president of Resonant Link, a startup company formed to commercialize his postdoctoral research. His research interests include electromagnetic component design, wireless power transfer, and energy harvesting. All yours, Aaron.
Thank you very much. Just give that to you. Awesome. Well, thank you guys all for being here today, despite possibly having an exam tomorrow. Hopefully some of the answers are embedded in slide like 50 or something. So there we go. Just a brief introduction to who I am. I grew up in Ann Arbor, Michigan. I attended Swarthmore College in Philadelphia. Went back to the University of Michigan to get my Ph.D. And I'm now working up in New Hampshire at Dartmouth. My interest in power electronics started when I was building an audio amplifier in my senior design project in college. I needed a 400-watt AC to DC power supply. So I went ahead and tried to build it, and unfortunately the MOSFET caught on fire. I don't know if you can kind of see there. It's not doing very well. So I decided I should go to school and learn more about this. And so as a
Burn it more carefully.
yeah, you want a slow burn so it lasts longer. You need at least 10 seconds of operation. As my PhD, I worked on energy harvesting, but at my postdoc, I've started working on magnetic components specifically. And today I'm going to be talking to you about magnetic component design within power electronic systems, and also a little bit about wireless power transfer as well. Power electronics are very important for many different systems throughout modern society. They impact transportation sector, which is increasingly becoming electrified. In communication systems, power electronics are crucial for data centers. And the list sort of goes on and on. And in many of these different systems, the power electronic performance is often the limiting factor, both the power density, the size, the efficiency, and the power handling capabilities. So improving power electronics is really important for many different systems impacting modern society. So a power electronic system, as many of you guys already know, comprises of 3 main things: switches, passive components, and control circuitry. So on the right here, I just have an 85-watt MacBook charger taken apart. What you can see the switches here we have, but what sort of dominates the layout of this board is the magnetic components. So we have a flyback transformer, we have a boost inductor here, we have EMI filtering, and these both dominate the physical size, but also dominate the loss budget. So if we want to improve power electronics, it's very important to reduce the size and increase the performance of the magnetic components. And this is true with more than just the MacBook charger. So here's an LED light bulb. Obviously, you have to do the AC to DC conversion, and then you see that transformer there, which is dominating the size, the physical size of the printed circuit board. And if we go to a wireless power transfer application, this is a demo board. You have a sparsely populated PCB on the left and this huge magnetic component on the right. So why is making magnetic components hard? I first worked on just scaling of magnetic components to understand why we can't just make them smaller and smaller. So in order to do this, we look at a fixed frequency. So we have a given application. And we're going to look at scaling the physical dimensions of the component, of the magnetic component. And I scale all of them by this factor epsilon. And I constrain the heat flux. So that means that the power loss of the component has to get smaller as the component gets smaller because there's less surface area. Otherwise, the component will overheat. And if we constrain the heat flux, we find a few different constraints. So one is that the power handling is proportional to the size cubed. So as the component gets smaller, you can handle substantially less power. And we also see that the loss fraction, which is the ratio of the power loss to the power handling, is proportional to 1 over epsilon, which means not only is the efficiency or the power handling going down, but the efficiency is going down as well. So making small magnetic components is very challenging. So to overcome this challenge, people propose increasing switching frequency. If we can increase switching frequency, then you have less required energy storage for the same ripple. And if we have less required energy storage, then theoretically we can make smaller and more efficient magnetic components. This sort of idea is enabled by new switching technologies that have come onto the market. So gallium nitride and silicon carbide devices have really low capacitances, can be switched at really high frequencies. And there's also been a lot of advancements in resonant circuit topologies that sort of enable this increase in frequency. So it seems like the problem's solved, and people are just sort of charging ahead. And I'm going to try to throw up a little bit of a caution flag here, in that there is a challenge in going up in frequency, and that is that winding loss or losses in the magnetic components actually increase with frequency. So it sort of begs the question: does the benefit of increasing frequency get offset by high frequency losses? So in order to answer this question, we have to understand what are the losses in a magnetic component, and there are two different types of losses. We have magnetic core loss, and we have winding loss. And we're going to look at each of these loss mechanisms and see how they scale with frequency to see if going up in frequency can provide a benefit. And we're going to start by looking at magnetic core loss. So here I plotted a bunch of different core materials. On the x-axis, we have frequency. On the y-axis, we have the power handling at a specific loss density. So more or less, this is the efficiency of the core material. What we see is we go from 100 kilohertz to 1 megahertz, we get almost an order of magnitude improvement in performance of the core material. If we go from 1 megahertz to 10 megahertz, we see a 30% improvement. So less improvement, but there's still something to be gained by that. So from this perspective, from the perspective of core loss, going up in frequency is going to still provide opportunities for miniaturization. So next we have to consider winding loss. So if we consider the simplest type of winding, which is a single layer solenoid.
Before you leave the first one, is there a limit to how much increase you can get? Is there some kind of physical limit that you know about?
For core, so they're basically the limit is what kind of core materials can be made, and they're trying to you need to create really small magnetic flakes that are shaped in the right direction. Researchers are trying to advance this. Right now, about 10 megahertz is about the boundary of the performance of core materials, but people are trying to make higher frequency core materials to even push this even farther. So now we're going to look at the winding loss as a function of frequency. So I said we're looking at a solid conductor where the conductor is much thinner than a skin depth. And now we need to be concerned with skin effects. So here on the left, we just have a solid conductor operated at DC. The pink just shows the current distribution. It's evenly distributed through the entire conductor. In this case, it is DC, but the AC resistance factor is 1. As we go up in frequency to 50 kilohertz, 60 hertz, and eventually 1 megahertz, you see that the current is charging just around the very outside of the conductor. In this case, the AC resistance over the DC resistance is 10 times, so we have 10 times the amount of loss. by going up in frequency. And so this creates a problem. It creates a huge problem. So to overcome this problem, you can use Litz wire. Litz wire is many thin strands of wire that are isolated and then twisted together. Because the strands are thinner than a skin depth, you get full conductor utilization, so this is really good. But you've also created a multi-layer winding since all of these conductors are now in parallel. So now you have to be very careful to mitigate proximity effect. So the AC resistance factor of Litz wire, a simplified expression is shown here, and there's two parameters that I want to draw your attention to. So in the denominator, we have skin depth. So as you go up in frequency, the skin depth is going to get smaller and smaller. So the AC resistance factor is going to go up for a given strand diameter. But in the numerator, we have strand diameter, and this is to the 6th power. So what this means is that if we want to go up in frequency, then we have to be able to use thinner and thinner Litz strands. The problem is that using really thin Litz strands is expensive. That's hard to manufacture. In fact, they're limited to about 32 microns. 48 gauge Litz wire is about as far as you can really get commercially. And so this is limiting our ability to go up in frequency. So to sort of put all of this together, Dave Peralt's group came up with this idea of a modified performance factor. So this is sort of the power handling at a specific loss density, but now considering both core loss and winding loss. And this first order analysis shows that at low frequency, the core materials aren't performing very well. At high frequency, the winding isn't performing very well. But around 1 megahertz, we're actually able to have low loss and get improved performance. So I wanted to, what this sort of brought up when I was thinking about this is, does this actually hold in a practical design? Because this is just a first order analysis. That analysis doesn't include the benefits of reduced inductance requirements as you go up in frequency. So I wanted to understand whether in a practical system that the benefit would be around 1 megahertz, or in fact we could push up into higher frequency and get more power dense components. So I went back to this MacBook charger. The MacBook charger uses a flyback converter to take the high voltage DC and bring it down to a low voltage. So I tried to optimize the flyback transformer at a given frequency, and then we sweep that frequency to see where we can get the most power dense component, and we're going to constrain a 40°C temperature rise. There's a lot going on here, but on the x-axis we have frequency, y-axis we have power density. I'm optimizing the transformer at each of these different frequencies to see where I can get the most power dense transformer. And I'm optimizing in terms of turns ratio, number of strands, gap size, those kinds of things. So there's two different types of conductors that I considered. I considered a single layer solid conductor, which we talked about having skin effect issues. And then I also looked at Litz wire. Just because of time, we're just going to focus on the Litz wire. What we can see is that the most power dense component was indeed around the 1 megahertz, sort of validating the first order analysis that Dave Peralt's group came up with. And the reason for this is because this is where the losses are minimized. And this can be seen on this plot. So now we're going to fix the size of the core and just try to minimize the losses for that given size core. So now I'm plotting losses on the y-axis, frequency we still have on the x-axis. And we see that the minimum losses are around 1 megahertz, and that exactly overlaps with the place where we're able to create the most power dense component. So now what we can do is we can say, okay, we'll have the same loss on the y-axis, we have frequency on the x-axis, but we're now going to plot two different Litz strands. So we have 46 gauge Litz wire is the blue, and the orange-ish color here is the 50 gauge Litz wire. What we can see is that we're able to significantly reduce the losses, which is what we thought would happen because of this AC resistance factor expression that we had before. And we're able to push up the operating point slightly above 1 megahertz because of this decreased strand diameter in the Litz wire. So using thin Litz wire strands is really important for decreasing losses at high frequency. Strand diameter is the limiting factor in terms of continuing to improve magnetic component size and performance. So there's interest in reducing the size of magnetic components, and that has spurred interest in increasing switching frequency. However, high frequency winding loss limits the promised performance benefit that could go up in frequency. Thinner conductors are required to reduce winding loss at high frequency, but they're only but commercially available lit strands are limited to 32 microns. Okay, so we went through some background on wireless charging or on magnetic components, and now what we're going to do is we're going to take that knowledge that we just developed about the importance of thin conductors and utilizing them well, and apply them to improving a wireless power transfer system. So that's where we're going to head next. And then once we do that, I'm going to talk a little bit about resonant power conversion if we have time, and then we'll have some concluding remarks and some future work. So when I tell people that I work on wireless charging, this is often what they come back with me and they say, oh, that's great. So I'm going to be able to like walk in my house and just run my vacuum cleaner without a cord. And that's not really what wireless charging is. Wireless charging looks a lot more like this, where you have your pad, you put your phone on it, and you feel cool because it's wireless, but the added convenience is you look around for it a little bit. So it would be nice if it provided life charging integration. It'd be nice if it could help with electric vehicle adoption, provide vehicle-to-grid energy storage or charge on the go. But all of these things are well beyond where wireless charging is today. So the reason for that is that the theoretical maximum efficiency of wireless charging is dependent on two factors: the quality factor of the coils and the magnetic coupling factor. So as you decrease the size of the coils or increase the gap between the coils, your magnetic coupling factor decreases. Therefore, the quality factor of the resonant coils is the key metric for wireless power transfer performance. Therefore, in order to increase the efficiency, increase the range, increase the power handling of wireless power transfer systems, we have to reduce the losses so that we can get a high Q. So here's the wireless charger that's on my desk that I use to charge my phone. I took it apart because I'm an engineer, and that's what you should do with things on your desk. They're typically made out of Litz wire and a capacitor to form the resonant coil. And the loss mechanisms, the first one is what we talked about at the beginning of this presentation, which is proximity effect due to the strand size limitation. There's also the performance of Litz wire only extends to the point of the termination. Once you have a solder joint at the ends of Litz wire, you no longer have many thin isolated strands. You now have a single blob, so now you suffer from skin effect, like we talked about earlier in the presentation. You also have its plate losses in the capacitor, which adds some additional losses to the system as well. So if we want to improve this system, we have to attack this problem. As we've said over and over already today, the strand size is a huge limiting factor. We need to be able to use thinner conductors to get high performance in a high frequency magnetic component. So it turns out if you go to your local Meyer, there's a really inexpensive conductor that's really thin, and that's aluminum foil. So aluminum foil in the store is 16 microns thick. It's really cheap. It's commercially available, and in fact, you can buy freestanding foil all the way down to 6 microns. However, if you just use a single piece of aluminum foil, you're going to have a high DC resistance, so we need to stack many of them in parallel. But if you stack many pieces of foil in parallel and put them next to a magnetic core, what happens is all of the current just crowds in the top layer of the conductor. It's following a path which is trying to minimize the inductance of the component. So you don't get equal current sharing, so you don't get any of the benefits of having thin conductors. So this isn't a solution. So we need a way to force equal current sharing. In Litz wire, that's done by twisting. So the top layer, sometimes the bottom layer, which is sometimes the middle layer. But that can't be done with foil. I tried twisting it, and I just ended up with a big ball. It's no good. I wouldn't recommend it. But if you, so we need a solution to force equal current sharing between these many thin layers. So what we're going to do is you could add an impedance to each of the foil layers, and by adding an impedance, you could force equal current sharing. If you added a resistance, you would get equal current sharing, but a lot of loss. So instead, what we do is we add a capacitor to each of the different layers. By adding a large capacitance to each of the different layers, you can force equal current sharing. But we can also use this capacitance not only to force equal current sharing, but also to provide the resonant capacitance, which is required for wireless power transfer. So how do we implement this concept? We implement it using something called the multi-layer self-resonant structure. And what it is it's C-shaped conductors with the opposite orientation. So this one's coming out of the board, this one's going into the board. And it's separated by a low-loss dielectric washer shape in between. We stack a bunch of these together, and we put them in a magnetic core. And how this works is, in order to understand how this works, we're going to look at a single section. So what happens is current flows around one of these conductive layers and gets to a gap. At that point, there's a displacement current through the dielectric down to the bottom conductive layer, where the current flows all the way until it hits the next gap, goes through the dielectric layer back up to the top. So what you notice is that we formed an inductive current loop, but also we've gone through the dielectric layer twice. So you get an inductor in parallel with 2 series capacitors. If we take many of these sections and we stack them on top of each other inside of this magnetic core, Each section's capacitance is inductively coupled together, and we form a single LC resonator. And because they're all inductively coupled together, there are no terminations. So we have both the benefit of forcing equal current sharing, but we also have the benefit of having no physical terminations. So if we go back to the conventional resonator, it was made out of Litz wire and a capacitor. We said the dominant loss mechanisms was proximity effect due to strand size limitation. Well, we no longer have to worry about that as much because now we can use foil, which can go down to 6 microns as opposed to be limiting to 30 microns. There are no longer any terminations in the high current path, so we've eliminated that loss mechanism. And we no longer have an external capacitor since the capacitance is integrated into the winding, so we no longer have any plate losses in the capacitor. So this is great. We went ahead and tried to build one. It turns out that handling really thin foil, there's some challenges behind it. Pretty quickly, foil looks like this. It's no longer very thin in the Y direction in that case because of the wrinkling. So we get increased loss, and you also get shorting between the layers. So we had to figure out a way to prototype this coil in order to demonstrate that this concept was possible. And so because it was really hard to handle, what we wanted to do is we wanted to be able to use a substrate to support the thin foil layers. So there are really expensive substrates to support layers, and they have really good dielectric properties, but obviously we don't want to use an expensive material inside of our coil. So instead we wanted to figure out a way to use PCB substrates. So your typical PCB board is made out of FR4 and then has copper on top of it. You can also get flexible PCBs, which are made out of polyimide and have thin copper on top of it. But the dielectric properties of both polyimide and FR4 are really poor, and so we don't want to integrate them into our structure. So our goal is to develop a new structure that incorporates this low cost but high loss substrate into the resonant structure without impacting the performance. So to do this, I developed the modified multi-layer self-resonant structure. And it's just a simple twist on the old idea. So you see between layers 2, 3, and 4, we have C-shaped conductors with opposite orientation separated by low loss dielectric. That's exactly like we had in the previous device. But now we have this sort of green-looking layer between layers 1 and 2. This can be FR4 and polyimide. And it's there to support the conductor, but the conductors around that section are oriented in the same direction. And because they're oriented in the same direction, no voltage is created across the capacitance between these two sections, and therefore no loss is created due to the dielectric properties. So if you look at an equivalent circuit model of this new modified structure, we can see that we have 2 dotted terminals of the transformer here, and this substrate capacitance between layer 1 and 2, the substrate capacitance goes between the 2 dotted terminals, so no voltage is created across this capacitor, and therefore no loss is created in this capacitor because there's no voltage potential across it. So with this new modified multi-layer self-resonant structure, I was able to construct a prototype. The prototype I had has a diameter of 6.6 centimeters. And I needed a way to compare it against the current state of the art. So I did some scaling analysis that shows that the quality factor of resonant coil is proportional to its diameter. And the largest, a figure of merit for a coil could be the quality factor divided by its diameter. And the largest QD, or quality factor divided by a diameter, that we could find in the literature was 28 inverse centimeters. So at 6.6 centimeters, that means we should be able to, the state-of-the-art coil should be able to achieve a Q of 185. So the multi-layer self-resonant structure achieved a Q of 1177, which is a QD of 178, or 6 times larger than the quality factor of a conventional coil using conventional coil. And this matched within 15% of our theory, which suggests that our modeling of it was correct. You can see here on the right, this is the impedance magnitude as a function of frequency. This is zoomed out a little bit, so between 7 and 7.15 megahertz. And in order to see the peak in the 3 dB fall off, we have to really zoom in to very fine frequency range in order to see the performance of the coil. So the design space is shown here. So on the x-axis, we have the number of sections, which if you think about Litz wire is kind of similar to the number of Litz strands that you're using. On the y-axis, we have conductor thickness. So remember way back at the beginning of the presentation, I talked about how important using thin conductors are. So if you had a 10 micron thick conductor, the largest Q you can get is about 1,000. If you were using typical Litz strands, you'd be way off this chart. It wouldn't even be feasible. But because we can use 6 micron thick copper, we're down here in the Q of 1100 to 1200, 1400 range. So we use 6 micron copper. It's laminated on 25 micron thick polyimide with flex PCB material, and we use 25 micron thick PTFE washer shapes to separate these two different sections. So we're operating in this space right here. So this is a picture of one of our first early prototypes. You can see the polyimide material that's supporting the laminated copper there. You can see it's in a pot core, and you can see the C-shaped conductor here with a small gap in between it.
Very old tuning that you did there for that circuit in terms of matching. Is that desirable to have such a narrow bandwidth in this kind of applications?
Yeah, so it's actually fundamental in the performance of the system is having really high Q. Once you load it, the loaded Q of the system will be lower, so it's a little bit easier to tune than I'm showing here. But the unloaded Q needs to be very high, and that's just indicative of the fact that the losses are very low in the coil. So here's a plot of, on the x-axis, we have the distance. On the y-axis, we have efficiency. So this is the wireless gap, or the gap between the two different coils. The dashed line is the state-of-the-art coil, and the red line is our modified self-resonant structure. We have experimental data to back this up. So this is experimental data that matches between the two, or that validates the red line. And what we found is that we're able to get a 2 times increase in range while maintaining above 94% efficiency. We're able to get 80% efficiency all the way out to 7.5 centimeters, and above 70% efficiency all the way out to 9 centimeters. And so what this looks like in a practical system, so here's a gap of 10 centimeters. Using these new coils, we can still get 65% efficient wireless power transfer. If you used a conventional resonator, you'd be having efficiency near 11%. So it's really, sort of extends the range of what's possible in wireless power transfer. So we got excited about this structure, but some of the criticisms that we got was that the height of the structure was too tall. So this original structure had a height of 1.62 centimeters, which is substantially thicker than my phone. So it's hard to think about the applications which that would fit in. So I wanted to explore the feasibility of creating a thin and high Q structure at the same time and quantify what is the trade-off between Q and height of the structure. So in order to understand that, we need to think about what is the trade-off between structure height and quality factor. And there's three parameters that get impacted when we start to think about reducing the thickness of the structure. So the first is if the backplate of the magnetic core is too thin, then we're going to get excessive core loss. If the winding area is too thin, then we're going to get excessive winding loss. And it actually turns out if the distance between the top of the winding and the top of the core is too thin, then we're also going to get excessive winding loss. And the reason for this is shown by a finite element simulation. This is a 3 millimeter tall pot core. And you can see that the field lines going through the winding are not parallel. So the conductor is only thin in this direction, right? This is many thin conductors. So we need the field lines to be parallel to the conductors. Otherwise, it's not going to look thin, and you're going to get large eddy currents in the conductor. So by having a significant gap between the top of the winding and the top of the core, you actually end up getting very parallel field lines, and this is one of the ways we're able to achieve very high Q. So this limits the minimum height of the structure. So I ran an optimization where I constrained the height to be 2 millimeters. I optimized the height of the backplate, the height of the winding, the height of the gap, and I found that the theoretical maximum Q would only be 345 for this very thin structure. And that's only barely, that's 3.3 times smaller than the previous design and only barely better than what a conventional resonator could achieve. So this is problematic. So we need a strategy to straighten the field lines around the thin multi-layer self-resonant structure in order to be able to achieve both thin and high Q. So I developed this thing called the modified pot core, and I realize now that I don't have a very good naming scheme if I just calling things modified, but I'll work on that for later. The The modified pot core has a ring of material around the center post and around the outer wall of the conventional pot core. And what this does is it actually reshapes the magnetic field so that it's parallel or more parallel to the winding and allows us to get a higher Q in a thin structure. And it significantly reduces the eddy currents. So the height of this ring doesn't impact performance, so we want to minimize what this thickness is here. But the width of the ring is a key parameter in terms of the overall system performance. If you make it bigger, you further and further straighten the field lines, getting higher performance. At some point, if the width is too large, then it becomes impossible to physically place the winding inside of the core. So that's a constraint and one that we can't exceed if we want to be able to build the winding. So in the designs, we select the width of the ring to be the width of the gap between the size of the winding and the core, and that way you can still physically place the winding inside of the core. I created a design space, an optimization space where I tried to optimize the space. I optimized the winding, the core, and the air gap. And this is for a structure height with a height constraint of 3.5 millimeters. And this optimization space is shown here. Where on the x-axis, we have the number of sections, which is akin to the size of the space allocated to the winding. On the y-axis, we have the amount of space allocated to the core backplate. And then obviously, any remaining area could be used for a gap between the top of the winding and the top of the core. This red area signifies constraints that aren't designs that aren't feasible, where the addition of the three heights violates our height constraint. What you see is that the maximum Qs fall right along the line of this feasibility boundary. And what this means is that we don't actually need any space for that gap anymore. With the modified core, you actually want to fill up the entire region with winding and core so that you're using all of that space for those two materials and not for airspace. And so this is really exciting. This means that we can get better performance in a much thinner region. For this design, the maximum quality factor can be achieved with a core backplate of 1.75 millimeters and about 10 sections or 12 sections. So I did this optimization over a range of different structure heights, ranging from 2 millimeters up to 5 millimeters. This is a single layer base case, which only considers winding loss in a single layer reference design. This is over optimistic for what can be achieved for a conventional resonator, but this is what we're going to use as a base case. The top is our structure in a pot core, so we get a 1.3 times improvement at this 3.5 millimeter height. But as we go down to this 2 millimeter height, we see that there's very little room for improvement using our multi-layer self-resonant structure. So finally, if we use our structure in a modified pot core, we're getting a 1.7 times improvement in this thin 3.5 millimeter, and we still get performance benefits all the way down to 2 millimeters. So in order to validate this plot, I went ahead and built a structure with a height of 3.5 millimeters. We're going to compare against the state of the art. The state of the art, people don't use height as a constraint, so we're going to stick with that same Q of 185, which is the largest QD I could find in literature, and use that as our reference, despite the fact that there's no height constraint in our base case. And this new thin multi-layer self-resonant structure achieved a Q of 560. So this QD is 3.4 times larger than what a conventional resonator can do. And this is despite the fact that we've now added a significant height constraint to the coil compared to conventional resonators. So this is, again, the frequency versus impedance magnitude plot, just showing that, in fact, we're able to get a high quality factor. And now we can look at the efficiency as a function of wireless range. And for the thin self-resonant structure versus the state of the art. And what we see is that we get a 3.7 times reduction in loss at a gap of 6.6 centimeters and a 1.4 times extension of range while maintaining above 90% efficiency. And this is while adding the constraint of making it thin enough to fit into most consumer electronics. So all of this wireless efficiency data that I've observed and shown to you so far was done at low power. So this is around 1 watt, and this is too low for many practical applications. So sort of begs the question is, what is the performance at high power, and what is the power handling limit of this new structure? So if all the losses were linear, then the efficiency would be independent of the power loss. We would get the same efficiency, but unfortunately there are some nonlinear power-dependent loss mechanisms versus that if you're operating at higher temperature, it's possible for the core loss to go up depending on the design of the core material. We also, as the temperature of the winding goes up, you're going to get increased resistivity. That increased resistivity is going to add to your winding loss. So that's something else that will decrease the performance. You also will get an increase in flux density. There's two different core loss regimes that you can be working in. There's a linear core loss regime and a nonlinear core loss regime. If you're most of the time in wireless power transfer applications, you're working in the nonlinear or in the linear core loss regime. But if you push the power high enough, eventually you're going to get into the nonlinear core loss regime, and then that's something that you need to be paying attention to. So I'm going to skip all of the calculations of how to get this, but just sort of show the idea of where we're operating at. We have power along the x-axis, efficiency on the right, and temperature on the left. So as expected, the efficiency is relatively constant at low power. Once we push up to above 10 watts or so for this really small, thin structure, the one I showed you before, the efficiency falls off from 84% down to 82% before we eventually reach our 40 degrees C temperature rise limit, and that's where we cut it off. So the power handling limit could be dependent on many different factors. It could be dependent on safety, and there's currently many studies being conducted on what are the safety limits of wireless charging, so I'm going to leave that up to them. It could be for core saturation, but in wireless charging, you typically have a very large gap, so core saturation is typically not an issue. It could be dielectric breakdown, but we're operating at high frequency, so we have a relatively thick dielectric layer, so this is also typically not an issue. So we normally run into a thermal constraint. So for this same thin structure that I was showing before, I limited it to a 40 degrees C temperature rise for the and compared the multi-layer self-resonant structure to a conventional resonator technology. We're able to get about 3.5 times as much power at a gap of 33 millimeters, and at a gap of 13 millimeters, we're able to get almost 7 times as much power before running into this thermal constraint. So I wanted to validate this plot, so I went ahead and did experiments at high power. So here's our two thin multi-layer self-resonant structures separated by 3.3 centimeters. This is a thermal image. This is our load, which is why it's so hot. We're dumping all of the power into those load resistors, and this is an image of the multi-layer self-resonant structure operating. And we were able to experimentally get 175 watts over 3.3 centimeters, which is 3 times more than other designs in the literature. And this is for 40 degrees C temperature rise with passive cooling. And again, this is for that thin structure that I've been talking about. So now we can go back to this plot and sort of put that on the plot. So this is the experimental validation for the multi-layer self-resonant structure. It's within 20% of the of what our analysis showed, which sort of gave us confidence in the trends associated with this plot. So the multi-layer self-resonant structure allows us to reduce losses and therefore can produce a high Q resonant coil. It allows us to get increased efficiency, range, and power handling while being constructed entirely of low-cost materials. We talked about 3 different improvements to this. We talked about the modified structure, which allowed us to use low-cost but high-loss substrates within the structure without affecting the performance. We talked about the modified pot core that allowed us to create very thin structures by shaping the magnetic field around the conductors. And we also looked at the power handling limits of the structure to see how it performed in terms of power handling. This idea extends beyond just wireless power transfer. It can also be used in other applications. So the multi-layer self-resonant structure can also be used in resonant power conversions as the LC tank. And this will enable high-frequency operation and increased power density and resonant power conversion. Increasingly, conduction losses are the dominant loss mechanism, especially in a resonant power converter, which puts all the onus of the performance on the passives as opposed to on the switches. And so there's a need for a high Q or low loss resonant tank and resonant power conversion as well. So all of the techniques that I talked about today can be applied equally as well to resonant power conversion as they can be equally as well to wireless power transfer as they can be for resonant power conversion. The one caveat is that you have fewer constraints in resonant power conversion in the construction of the device. And so this allows us to actually create either a series or a parallel version of the exact same resonator. So here's a series version of that resonator. We have the thin foil layers. There's capacitance between the two. You form one inductive loop around the side, and now you have a series resonator as opposed to a parallel resonator. And many of the resonant circuit topologies actually depend on using a series resonator. So that is exciting. We can still use the modified version of this structure to support the thin layers on flexible PCBs. You can still use magnetic core placement magnetic core material to shape the field and reduce the loss around it. So just to demonstrate that the idea works, this is the series resonator built for this application. It's used, we're using the modified structure, so it's copper laminated on polyimide again. We used a simple block ferrite, so the performance isn't quite as good because we don't shape the field quite as precisely, but it demonstrates that the idea works. We can see that with no core, actually a single layer reference design was better, but once we shape the magnetic field properly, we're able to get a 1.6 times improvement in quality factor compared to a single layer reference design. So in fact, this can be used for resonant power conversion. So the multi-layer self-resonant structure is a tool that can be used in many different applications. It can be used for wireless charging. It can also be used for resonant power conversion. It can be created to be both series and parallel. And the experimental Q in this application was 1.6 times larger than benchmark. So way back 45 minutes ago, I said that there was interest in reducing the size of magnetic components. This has spurred interest in increasing the switching frequency. However, high frequency winding loss limits the promised size and performance benefit. And in order to overcome this, we need thinner conductors are required to reduce winding loss at high frequency. And commercially available Litz wire is limited to 32 microns. Well, the multi-layer self-resonant structure is one answer to this problem. It reduces winding loss by forcing equal current sharing between many thin foil layers. It allows us to produce extremely high Q resonators, and it has applications in wireless power transfer, where I showed it could drastically increase the range, the efficiency, and the power handling. It also has applications in resonant power conversion, where it provides an opportunity to increase power density of power electronic systems. Thank you very much, and I welcome any questions if you. Thank you.
How do you do scaling up here in this application?
Scaling up in terms of what?
What?
Yeah, so it works very well, actually. It's, in fact, easier to design at bigger sizes. Can you click on this link for me for the electric vehicles one? So this is a design that I did for EV charging. So this is a coil that has a diameter of 30 centimeters. We're looking at a gap of 10 centimeters. This is right within where the Qualcomm Halo system is operating at. Our system, we can get a Q of about 1800 with this coil with only 6 layers of foil. So the cost of producing this is extremely low. The coil-to-coil efficiency is above 99% over this gap of 10 centimeters. And the passive cooling limit for this system is shown here. People talk about 10 centimeters being the gap of interest. And so we can passively cool this coil while powering over 10 kilowatts of power. If you add an active cooling, this could go up drastically as well. So we're currently, right now, we're building this prototype is being constructed to validate that high power performance. Thanks. Yeah.
You mentioned in the part where you have the modified pot core, it's desirable to have the ring on the top to extend further in as much as possible.
Mm-hmm.
So you have your magnetic lines flatter, parallel to the winding.
Mm-hmm.
But then you cannot drop your windings in. Would it be possible to make the modified pot core as a two-piece so that you can drop your winding in and then close?
Yeah, absolutely. And that is 100% true. We can do that. So this gets at your question. So this is a plot where the width of the ring is increasing along the x-axis here. On the y-axis, we have the quality factor. So increasing that width helps and helps and helps to a point. At some point, it actually starts to go back down. So I was trying to save time by just giving that as a reason, but there's increasing this width only helps to a certain point, and at some point it starts to hurt. The compromise of making it the same as the gap makes it both easy to prototype and gets close to the optimal performance, but you should make it slightly bigger, and using your idea that is possible, yes.
Probably a related question, so Tom, give me one. Did you look at any other shape instead of having these rectangular shapes? Like, will that be helpful? So say, for example, I'm going back to some of the experiences we have for Urbana and so on. If we have sharp edges, the field lines tend to be not behave nicely. But if we have round edges, probably it can be better.
Yeah.
Have you looked at that?
Yeah, so we did. So actually, the constructed version of this coil has this is a rounded edge. We found from our simulations that the performance in terms of core loss was essentially it didn't matter. That the flux concentration around that edge made only a very small difference in the performance of the core. In terms of actually producing this really sharp edge, it was physically hard for them to manufacture that, and so that's why we ended up getting the round edge. And this simulation suggested that both were fine, and we got our results matched that as well. Yeah.
Thank you for a wonderful presentation. That's a very impressive work. I'm curious, what is the bottleneck for heat transfer in your structure? Because you're doing natural convection. Is it the actual external platform, or is it you have trouble getting the heat out of your structure?
Yeah, so the hottest part is the winding. So as you get thicker and thicker dielectric layers, you start to get layers in the middle that are creating hot spots, like you're saying. And so that is a problem. And then there's the reason we chose natural convection was sort of to show off the performance of the coil. So adding some sort of cooling to the core, or adding another thing that we're considering doing is, so normally you would want to just make the dielectric layers thick for it makes it easier to handle, but obviously it impacts your thermals. So in doing an optimization where you make sure you're staying within your thermal design, but still have something you can handle is something that we need to consider as well. And it's part of the developing design process.
Yeah, maybe opening up the design space for other materials.
Yeah.
For both the conductors and for the
Yeah, and so the biggest one is the heat through the dielectric is the biggest constraint. But we really need, in order to get Q's, like the Q of the material is an upper bound on the Q of the performance of the structure for the dielectric material. So it's really important to use a low loss dielectric. So that sort of like limits you to polypropylene, PTFE, those kinds of materials. As soon as like a polyimide, for example, has a Q of 600, so that would be an upper bound on your performance, and obviously we can exceed that. So we have to be careful about what material.
Do you see opportunities for this? So like we use sometimes on our circuits inductive couplers for power transfer to like power gate drivers, isolated gate drivers. Do you see opportunities for this for like integration, or lithographic integration to do power transfer?
Yes. Yeah, I think so. I mean, the smaller you make it, the harder and harder it gets. Just to like get the capacitance you need. So depending, if you're trying to switch at 6 megahertz and do it in something like this small, that there'd be some challenges behind that. The other nice thing about the wireless power transfer application is you get there's a circuit somewhere here. You get a huge amount. Oh yeah, okay, this will do. So this is an equivalent circuit model of the two coupled coils. So the key thing about wireless charging is you have a huge amount of power that's fluctuating back and forth between this inductor and capacitor. But actually what's coming in from the input, the amount of power here is relatively low. So basically the power factor is really poor in a wireless charging system. And so having the fact that all of this is internal and there are no physical connections is the reason that this works really well. So you still have to connect to the coil. That bottom layer still has a physical termination. That's why we model this input resistance. But this input resistance doesn't affect your performance in a wireless charging system because the power flow is just back and forth between these two components. If you start to have the input power be a large fraction of the amount of power that's oscillating back in here, the benefits of the structure are still there, but they go down substantially. Yep, yeah, great questions. Yeah.
The heating issue. So it seems like a lot of the heat that you need to extract is basically in the axial direction along the plates, because you have windings stacked against one another.
So vertically throughout the structure, yeah.
So along the height, would it be possible to actually have sort of very small perforations so that you can have airflow going across it, as in along the height?
Yeah, you could, especially in the dielectric layers. The amount of this isn't a constraint that we've really bumped up against very hard. So the temperature difference in that coil with 12 sections was about 10 degrees C between the bottom layer and the top. And so we're able to push that pretty hard. As we go to the electric vehicle applications, we're cutting the number of sections in half, which means we have even fewer dielectrics that we need to go to. If it became more and more of a problem, then we could start to consider solutions like that. You need to make sure that you don't have breakdown of that air. Like if you have an air gap between the two foils, you do have a large voltage there, so the dielectric is keeping it from breaking down. So if you decided to puncture holes in there, you'd have to make sure that you're still operating in a safe regime. But yeah.
One more question.
Sure, yeah.
So if I go back to your previous presentation in the first half,
Oh, yeah.
you said something about Dave's group. They worked on some theoretical analysis where 1 megahertz was supposed to be a good area to operate these converters.
Yes.
Where the loss is, I think it was minimized.
Yep.
You guys did a prototype on to prove that basically that's possible.
Yeah, so that was sort of the sweet spot of core materials and winding loss. Using Litz wire in the conventional constraints is about 1 megahertz is where we find that threshold sort of like balances.
In your setup now, what the frequency will be a good frequency go and operate?
Yeah, so for wireless, so this is a solution for that problem in one space, right, in this resonant space, and now we can push up to basically the boundary of what core materials can do. So we're talking about up to about 15 megahertz. So between 6 megahertz and 15 megahertz, this can be operated. This new technology can be operated very well. Above that, so we're using a core material called 67, and above that, the performance of the 67 material tanks, and there aren't too many options to get.
Because that design was limited at high frequency beyond 1 megahertz because of your winding losses.
Yes.
This technology stuff is basically reducing the winding losses.
Yes.
Go farther down the frequency.
Yes.
But now you're saying why the core is again coming back.
So this is sort of goes. This is a question that he asked earlier, where I had that plot. He's like, "Oh, can the core loss? Does it continue to get better as you go up and up in frequency?" And the answer is only to a certain point. At some point, the technology of making core materials is diminishing, and so that's no longer a benefit for the core material to go up in higher frequencies.
Thank you.
Yep.
Any other question, guys?
I guess one quick question. Do you see the implication of this being more of an air core type topology, or do you think that there's a completely different optimization problem when you're looking at an air core?
Yeah. So it's for this technology for this multi-layer self-resonant structure. There's the way to do an air core is to do not a solenoid shape. A ring. Ring. I don't know the ring set. So there's a way to do this, and that way in that case, the way that you would shape the conductor would be that they would always be parallel to the field lines, and so then you wouldn't need to use the core to follow the field lines. So right now, the core is essential for shaping the field lines. If we could go to that round shape, then we could get away with that. The reason we haven't done that yet is because the construction challenges of doing that is there. But the benefit of what you're saying is real and is possible.
What is competing with your development? Who else is working in this space?
Yeah, so in terms of magnetic design, there's not too much. There's some people are tweaking Litz wire designs, are working at low frequency, different architectures in terms of coming up with arrays of windings and things. But in terms of really high Q structures, we're sort of out there right now on an island without too many competitors. I'm sure that's going to fill in around us as the more we present this. But from a performance perspective, there isn't really much of a competitor.
In non-magnetic areas, who is competing?
Oh, you mean in terms of wireless?
Yeah, in terms of wireless charging.
Yeah, I mean, there are other types of, there's far field where you're directing magnetic field waves. There are different antenna designs that are competing technologies. From a business perspective, the biggest competitor is actually just not doing wireless charging. So a lot of like Tesla's developing a snake. Some people just say, okay, well, let's just have people plug them in. It's not that big of a deal. So from the business perspective, it's really about how can we make the cost of this system low enough that the convenience it adds is worth it. And that's right now what I would say is the biggest competitor. Right now, from a cost analysis, maybe I can skip, well, if I go to the end, basically the Qualcomm system, to produce 2 coils, the amount of Litzwire, the amount of core material it takes for them, it costs about $900 to produce those 2 coils. So we have no Litzwire. The amount of cost it is for the winding is about 50 cents of winding materials. So the overall cost of building one of our cores is just how much it costs to make a core. So we're talking about $90 to make 2 coils. So it's about an order of magnitude decrease in cost. So that starts to make it a viable from the both performance and from hitting people's targets and convenience level. So.
Thank you, everybody.
Thank you. Thank you for your help.
You're welcome.
Ended up just like flipping